In order to describe the spread of our distribution in a consistent way, we need to bridge the gap between, on the one hand, a single number, the standard deviation, and on the other hand, this data range that we visualized on our histogram. And to do this, we first focus our attention on this second part, this data range, and we will make it more quantifiable and more consistent. This brings us to a new statistic about our distribution, namely the percentiles. And instead of giving you a general and thus vague definition, we will start out with an example. Let's say that your team needs to hire an additional data scientist. Now, because of budgetary reasons, you are required to hire a new candidate that is fresh out of college. Now, therefore, the only quantifiable measure to judge a candidate is by its GPA, its general point average in college. So let's say that you get a student and you need to judge whether it's a good hire or not. And you see that this student has a GPA of 4.1. Now the question, of course, is, did she do well or not? Now, never judge a single number in isolation. Always ask for more context. And thus, after some digging around, you find that the average of GPA at this college was 3.0. And additionally, that this was probably a normal distribution. So then you might conclude that indeed 4.1 is a very good result. However, I would stop and think about it. In fact, I would ask about the spread of this distribution. Was it a very peak distribution or was it a very broad distribution? Now you might ask yourself why this is so important. Well, I would argue that depending on the spread of this distribution, the student did either well or exceptionally well. And to see why this is the case and to indicate that the spread of a distribution is very important, I simulated two scenarios. One with a very small spread, so a peak distribution, and the other being a very broad distribution. And these are the histograms. So we have two normally distributed histograms, each with a mean of exactly 3. On the left-hand side, this red line is the mean, and on the right-hand side, it's also the mean. The only difference between these two distributions is their spread. On the left hand, we have a much more peaked distribution, and on the right hand, we have a much broader distribution. Now, the result of the student is indicated by this vertical dashed line, a GPA of 4.1. Now, just from visual inspection, we can see that the student did much better in comparison to her peers in the left distribution than in the right scenario. Why is this? Because in the left distribution, a value of 4.1 is much further along in the right end of the tail, meaning that a much larger group of students scored equal or less than this candidate. Whereas in the right distribution, there are still a lot of people that scored higher than a GPA of 4.1. And the need to quantify this visual observation directly brings us to percentiles, namely, what percentage of other students scored equal or lower than the student that we have in front of us. And this is exactly what a percentile expresses. Now, before we get into more detail about the percentiles and to visualize them on the histogram, let's look at the code that generated these two graphs. All of the code in this notebook cell we did before already, so I'm not going to go over it, instead of just pointing out that it does indeed give us these results. Now, if you do want some information about this code, there is of course always this Code for Data Science YouTube channel, where I upload videos where I go over each notebook cell in this course line by line, explaining everything that's going on. So let's now go back to the slides and see what we can learn about percentiles and how we can visualize them. And let's start by being very clear what the percentile of a distribution actually represents. And again here, I still refuse to give a general definition because they always end up being very vague. Instead, let's look in specific to the 90th percentile. The 90th percentile is the value of the data point for which 90% of the values of our distribution are equal or lower than this data point. Or said equivalently, for the 90th percentile data point, only 10% of values are larger than this value. Now conversely, the data point at the 10th percentile is the value of this specific data point for which only 10% of all the data points in our dataset are equal or smaller, and thus 90% of our data is larger than this value. Now we can visualize this by drawing shaded areas on our histogram, and these areas will include all of the data points that are smaller or equal to that specific percentile. In this first row of histograms, we represent the 90th percentile. In particular, we plot on the histogram a shaded region which encapsulates the 90% lowest data points, and thus all of the values outside of these shaded areas correspond to the 10% highest values. In the second row, we have the converse. The shaded area contains the 10% lowest points, or all of the values that are equal or lower than the 10th percentile, and all of the values that are outside of this area are of course the 90% largest values. Now to be clear, the 90th percentile itself is not a range of data, but instead a single number. It's the value of one single data point. And let's see how we can now compute this value and how we can make these plots. And again, we go to the code to find out. And as you will probably notice, the more we progress through this course, the more familiar the Python code will be. Now in this case, we first generate two populations, and I again decided to generate these populations using this skew norm function. Population 1 will be a skewed random distribution of 100,000 random points. Population 2 will be a non-skewed normal distribution, but also with 100,000 points. Now, of course, if you prefer to work with the familiar numpy.random.normal function to generate your populations, I put here these two populations in a commented line. So if you prefer to use these, you can just uncomment those and comment the other ones, and the rest will be exactly the same. In the next step, we just, per usual, compute some basic statistics for both population 1 and population 2. We compute the mean, the standard deviation, and the variance. And the reason for doing so is because later we will make a table with this extra row being the data interval, but that is for later. And then we get to defining or computing the percentiles of our two populations. And similarly to the other basic statistics, we don't have to do any of the calculations ourselves because there are built-in functions that do this for us. For instance, if we want to calculate the 90th percentile of population 1, we just type numpy.percentile, we give the Python array that contains our population 1, and we just give the percentile that we want Python to compute. In this case, percentile 90. Now again, I want to stress that the percentiles are singular numbers, and therefore this function right here will return a singular number, namely the specific value of population 1 for which 90% of the other values in our population are equal or smaller than this specific value, and that will be our 90th percentile. We can do the same for population 2. We can compute the 10th percentile of population 1, and we compute the 10th percentile of population 2. And now that we have our percentiles, we can plot these shaded figures on our histograms. And to do so, we will again make use of subplots. In this case, 3 rows and 2 columns. And the last row of these 3 rows will be for the next lesson. Now, in the first row, we want to visualize on our histogram the area containing all of the values that are lower or equal to the 90th percentile we just computed. And we will do this for population 1 and for population 2. Now, first of all, of course, we need to plot the histogram of our population. And this is very straightforward, of course. .hist, population 1, the number of bins, just to change things up, will be 40 in this case, and density is equal to true. Now we also want to visualize our mean of our population, so we add a vertical line at the position mean pop1, the mean of population 1 that we computed. The color is dark blue just to make it stand out. And then, to make the shaded area that we want to visualize on top of our histogram, we will use the function .xvspan. Now what this function allows us to do is to make a rectangular shaded area which spans the entire y-axis. So going from the bottom of the graph all the way to the top of the graph. And now the width of this rectangle is determined by the parameters that we choose. Now, of course, we want to make it go from the minimum value of our population 1, which is also the 0th percentile, and the maximum value of our shaded area will be the 90th percentile of population 1 that we computed. Now, this means that inside our shaded area will be all of the values between the lowest value and the 90th percentile, and thus the 90% lowest values of our entire dataset. We choose the transparency to be 0.1 and the color to be blue. Now, additionally, we want to actually represent the value of this 90th percentile in our histogram, by which I mean in the legend. Now, to do so, again, we will use an F string as our label. So the F string will be 90th percentile, meaning all of the values that are smaller or equal to, and then we use curly brackets to just round up to 3 decimals the value that we found, the 90th percentile of population 1. And of course, to have this label onto our figure, we need to explicitly add a legend. And here we also tell where this legend should be, on the upper right in our panel. And the exact same thing can be done for population 2, still on the same row of our subplots. And of course here, our shaded area will be from the minimum of population 2 to the 90th percentile of population 2 that we computed, and thus containing the 90% lowest values of population 2. Now, for the second row on our subplots, we want to again do the same for population 1 on the left and population 2 on the right, but now for the 10th percentile, meaning we want in our shaded area to have the 10% lowest values. To do this, we again plot our histogram of population 1, we add the mean of population 1 as a vertical line, and then our xv-span will now be from population 1 minimum, which is the same as in the first row of plots, but now of course it must stretch to the 10th percentile of population 1. And the same we do for population 2 on the right of this panel. Now the bottom row of plots will be for just a minute, but if we run this cell already now, we see that we get indeed, apart from this table, which we will come to later, these first 2 rows in our subplots. Now, in addition to this visualization of the percentiles, we actually have the numerical values in the legend of each panel. We see that for population 1, the 90th percentile is equal to 1.643, and that's this most right value of the shaded area. Now, this value means that for population 1, 90% of all of the data is lower or equal to 1.643. And likewise, for our normal population on the right-hand side, 90% of data will be smaller or equal to 1.285. Now, the same can be said on the bottom rows. The 10th percentile of our population 1 is 0.121. And for our normal population, the 10th percentile is minus 1.274. And this is how we can use Python code to generate and compute the percentiles of our data distribution. Now, how can we use these percentiles to make yet a new statistics of our distribution, namely the data interval? Because the data interval is so closely connected to the percentiles of our distribution, there is again no need for a vague general definition. Instead, we introduce the concept by looking at an example. The 80% data interval is all of the data that lies between the 10th percentile and the 90th percentile of our distribution. Now, how can we rephrase this and use words that relate to the underlying data? Well, the best way I can think of is that the 80% data interval is all of our data in our dataset except for the 20% most extreme values. We throw away the 10% highest values and we throw away the 10% lowest values. And this is what the 80% data interval means. And then of course, you can generalize this example. For instance, the 95th% data interval is all of our data, except for the 5% most extreme values. We throw away the 2.5% largest values and the 2.5% lowest values. Now let's go back to our notebook and see how we can visualize this data interval. And we start where we left off. Namely, we made these figures where we generated these shaded areas on top of the histograms based on the percentiles of our distributions. And let's focus our attention on the left column, on the skewed distribution. In the top graph, the shaded area contained all of the values that are lower than the 90th percentile, and thus the 90% lowest values. But this means that it excludes the 10% largest values, and it is immediately what we need for our 80% data interval. And in the bottom graph, we shaded the area containing all of the values that are smaller than the 10th percentile, meaning the 10% lowest values, which is also what we want to exclude in our 80% data interval. Thus, the area that we want to shade to indicate our 80% data interval has to start on the left-hand side from the 10th percentile, and on the right-hand side, it has to end at the 90th percentile, because in that case, we exclude the 10% largest values and the 10% lowest values. And what we get if we do that is these graphs right here. We see that on the left-hand side, our shaded area indeed starts at the 10th percentile and it ends at the 90th percentile. And to generate these figures, it's very straightforward because we already know how to color these shaded areas and we've computed the percentiles. So let's go to the code and see how we do this. And these two last plots are plotted in these lines of code. We first plot the histogram of population 1. Then the XV line is the vertical line indicating the mean of population 1. This is just exactly the same as before. And now we use this XV span to make the shaded area. And we remember that it needs two parameters, where it starts, in this case, the 10th percentile of population 1, which we computed above, and it needs to end at the 90th percentile. And to get the numerical values of our 80% data interval, we put them into our label, again as an F string. In this case, a 80% data interval, or any data interval, requires two values, a lower bound and an upper bound. As the lower bound, we take, as a rounded value, the 10th percentile of population 1. And as the upper bound, we take the 90th percentile of population 1. And in this way, we represent our 80% data interval, just arranged between the 10th percentile and the 90th percentile. The same we can do for our population 2, the normal distribution. Here, our shaded area will be between the 10th percentile of population 2 on the left-hand side and the 90th percentile of population 2 on the right-hand side, and thus containing 80% of data that is closest to the mean. Now what we can also do is make a table that contains all of these statistics, but now also the data interval. So again, we make a data dictionary with a population as the key, and the values are just all of the population statistics. The mean of population 2, the variance of population 2, the standard deviation, and now also including the 80% data ranges. So on the left-hand side for the lower bound, the rounded 10th percentile, and on the right-hand side, the upper bound, the rounded 90th percentile. Then we again put it in a data frame and we display it. And what we see is this data frame. The mean is 0.02, the variance is roughly 1, standard deviation is then also roughly 1, and the 80% data interval lies between minus 1.278. Now, if you have good memory, then you remember that this is the 10th percentile of the normal distribution, and the upper bound is 1.278. Now again, because this is a population, which is still an approximation of the underlying theoretical curve, if we run this cell again and again, these values, they vary slightly. But now, in addition to the mean, variance and standard deviation varying slightly, also the 80% data interval varies slightly, meaning that the percentiles are just as much statistics that will vary from sample to sample, or if your population has a finite number of points, also the population. So let's now go back to the slides and see what we can also learn from the data interval. The data interval, as we set out to look for, gives a measure for the spread of your distribution. Let's say that you would have two normal distributions with an equal mean, but a different data interval. And this is very similar to the scenario of the student that we wanted to hire. On this first graph, we can roughly see that between the values 2 and 4 lies a lot more of the data of our dataset than on the right-hand side. On the right-hand side, we would roughly say that between 2 and 4 lies 80% or 85% of the data, but on the left-hand side, we would say that between 2 and 4 lies even 99% of the data. And now translating this to the language of data intervals, the 80% data interval for the left distribution will be a much more narrow range of values than the 80% data interval of the right scenario. And it is in this way that the data interval gives a measure for the clustering around the mean of our distribution. And then, of course, as we just saw in the code, the data interval and thus the corresponding percentiles are just additional statistics of our distribution, which we can add to our list of basic statistics. And the same dynamics apply between sample, population, and theoretical values. And before we conclude this lesson, let me briefly talk about a percentile that you knew all along, probably even before you started this course. And this is the median. Now, the median is the 50th percentile, and it's a good exercise for you to convince yourself that this is the case. So now that we have a firm grasp on percentiles and data intervals, let's remind ourselves that we were looking for a consistent way to describe the spread of the normal distribution by bridging the gap between, on the one hand, a single number, the standard deviation, and on the other hand, a data range. And now we know that this is the data interval. So now that we have the tools, let's look how this is done.